Okay, we've been talking about calculating probabilities and probability distributions of random variables and calculating the probability that a random variable will be in various ranges. And that's all great. There are situations where calculating the probability exactly is just incredibly complicated or time-consuming or in effect impossible. And in that case, it's useful to have some approximations for the probability. And what this chapter is about is 3 different kinds of approximations. The first approximation, really is it's an approximation to the distribution that says that the probability histogram of some random variables can be approximated well by a curve. And that particular curve that we're going to talk about is the normal curve, which if you've had statistics before, you've seen it. We'll talk about when that approximation is good, when that approximation isn't good, what kinds of random variables that applies to. The other 2, quote-unquote, approximations are really they're not approximations in the same sense. They're bounds. Just like Chebyshev's and Markov's inequality we had for lists, there's an analog of Chebyshev's inequality and of Markov's inequality for random variables. And in both of them, you basically are just changing the word mean of a list to the expected value of a random variable, and standard deviation of a list to the standard error of a random variable. And other than that, the definitions are exactly parallel, and in fact, the proofs are basically the same. So we'll get there today, but first let's talk about the normal approximation to the probability distribution of the sample mean and sample sum of draws from a box of tickets. So this curve here is the normal curve, and it has the equation y is equal to 1 over the square root of 2 pi e to the minus x squared over 2. Now, what I want you to, I don't care whether you memorize this or not, but what I want you to recognize is how it depends on x. It depends on x only through the value of x squared. So if you plug in x and you plug in minus x, you get the same value for y. It's symmetric. Okay? The other thing you should notice is e raised to a negative power gets smaller and smaller and smaller the bigger that negative power is, right? So the maximum value of this occurs when x is equal to 0. So this thing is a bump at 0. It's symmetric, and it gets smaller and smaller and smaller the further away you get from 0, right? Now, in order to go, if you notice that this curve that's plotted here isn't centered at 0. It's centered at 6, okay? There's been a change of variables. What's happening is that we're really thinking about things in terms of standard units rather than in terms of the original units. So this curve, I could, I'll phrase it the other way around. The curve is a good approximation to some probability histograms if first you transform the random variable to standard units. Now, what is standard units for a list of numbers? That's a concept we've had. We don't have standard units for random variables yet. But for a list, how do you change a list to standard units? Okay, so you take the original value minus the average of the values, the mean of the values, divided by the SD of the list. Right? That's how you take a value and put it into standard units for a list. Yes? For a random variable, the way you change values of a random variable into standard units is quite parallel. It's the original value minus the expected value divided by the standard error. Okay? Yes? This is how you turn a random variable into standard units, values of a random variable. Okay? So to put, it's the variable minus its expected value over the standard error. So if I take x minus the mean of x and divide that by the standard error of x, that's a new random variable, right? It's a function of the old random variable. What have I done to it? I've subtracted something and I've scaled it. Yes? I can actually write that as 1 over the standard error of x times x minus the expected value of x over the standard error of x. Yes? Did I do that right? This is a constant times a random variable plus another constant. Yes? This looks like a times x plus b, where a is 1 over se of x and b is minus e of x over se of x. Yep. Now, what's the expected value of a constant times a random variable plus the constant? Remember, one of the properties of the expected value is that the expected value of an affine transformation of x is that same affine transformation of the expected value of x. Okay, so the expected value of this it's always the case that the expected value of ax plus b is equal to a times the expected value of x plus b. Yes? That's true. So in this case, what's the expected value of 1 over se of x times x minus e of x over se of x? On the right-hand side, no, this is that times that minus that. The expected value of a sum is the sum of the expected values. The expected value of a constant times a random variable is a constant times the expected value. So this expected value of a sum is going to be the sum of the expected values. The first term, the expected value of a constant times x, is a constant times the expected value of x. And the second term is already a constant. The expected value of this is just itself. Okay, so these terms are equal, right? This is just 0. All right, remember, if you take a list and you convert the list to standard units, the mean of the new list is 0. If you take a random variable, you convert the random variable to standard units, the expected value of the new random variable is 0.